Hello, everybody, and welcome to all of you who are not here. I'm terribly sorry that I had to move the teaching time to this morning. I realize this is probably convenient for no one, but this is still an important class, and I'm hoping that everybody will watch the recorded video, and I'll give you lots of reminders to do so. Let's get started. Element of the day, carbon. Carbon is an element that most biggest stars like ours, even though we think of Sol as being a kind of modest star, can forge before they die. However, stars like Sol tend to hold on to their carbon. Most of the carbon in your body is from some kind of supernova, of which there are many different types, and we'll get to that. So at the time when our star dies, when it swells up and becomes a red giant, it's going to be making carbon, but it's not going to let go of it. But when a star explodes, it does release its carbon. Carbon is primarily useful because it can make 4 bonds. Most elements can only make 1 or 2 bonds, and a few can make 3. Only carbon and elements below carbon in the column on the periodic table of elements can make 4 bonds. So as far as that goes for you, look at the periodic table of elements, then look 1 down. The very first element beneath carbon is silicon. That's why computers have silicon as the basis for how they work, because silicon is as useful as carbon. It's just less common. So this is why you're a carbon-based life form, because carbon can make a bunch of bonds. It's an excellent backbone for building structures. Plus, carbon is super common. Almost all stars make carbon, even though only a few of them blasted away from them when they're done. And remember, every element in the universe, except for hydrogen and helium, comes from a star that's exploded in some way, shape, or form. Today is kind of all over the map in terms of covering topics. This is going to be true for a while because there's lots of little things that need to be included in an astronomy course, and you kind of just have to pile them together. There is, however, one huge topic that's going to come up again and again and again, and that's HR diagrams. And spectroscopy we've already talked about, but we're going to do a little tour through it again. And parallax we've already talked about, but you can never talk about parallax enough because parallax is super important to astronomy. And we're going to talk about binary star systems and how you can determine if there is a binary star or not. Because most star systems are so far away that when astronomers look at the light from the stars, we only see 1 star. And yet frequently, more often than not, there's more than 1 star there. How can you tell? Well, there are tricks that one can employ to determine what's going on. So we say nearly all the light we see when we look up in the night sky is due to starlight. I somewhat regret that slide because when the moon is full, the moon outshines all the stars put together handily. But if the moon's not in the night sky, then the light that you see is definitely starlight. And stars do indeed have colors. Here, someone's taken a very stable camera and put it on an extremely long exposure. Looks like about 2 or 3 hours worth of time based on how big the arcs are. And the colors of the stars slowly comes out. Stars range in color from bluish to reddish. And there are some stars that are so cool that they are emitting primarily in infrared. And some stars that are so hot that they're emitting primarily in ultraviolet. Although if you're emitting in ultraviolet, you're also emitting a ton of visible light. So they're highly, highly visible to the human eye. When we look at faraway galaxies, we are seeing the light from billions of stars all adding together to make a kind of amorphous glow. Of the many reasons that we can pine for the old days when there was no pandemic, surely one of the worst ones is that I can no longer point a telescope at Andromeda for you. But if I did, this is what you would see. A kind of a fuzzy blur. As a matter of fact, there's a lot of things in the night sky that only show up as kind of a fuzzy blur when you look at them. Consequently, astronomers didn't know for a long time what they were. This is an exceptionally good picture of a galaxy, and you can only get that kind of picture with a telescope that's looking at the galaxy for a long time, so it acquires a lot of light, so you can make out a lot of features, and you can digitally store the information and keep on adding it together and adding it together and adding it together until you can finally see what's really there. So basically, until astronomers got a hold of CCDs, charge coupled devices, same kind of camera that's in your phone, we couldn't get a really good picture of a galaxy. What we could do is take a photographic plate and let it be exposed for a long time, but it doesn't give you nearly as sharp an image as this. Our own galaxy, the Milky Way, is shaped like a spiral dish, and it contains about 100 billion stars. And every time you see a picture of the Milky Way, it's a bit of a lie. The sun is towards the outside of the Milky Way, and we have a really hard time seeing through the center. There's a lot of dust in the plane of the galaxy, and that dust really interferes with our ability to see through it. We can see other galaxies far more clearly than we can see our own, at least the far side of our own. And so much of what we know about the galaxy is about our galaxy, the Milky Way, is guesswork. Indeed, you can find astronomers that disagree about exactly how many spiral arms the Milky Way has. So if we're not in 100% agreement on how many spiral arms the galaxy has, then it's fair to say that we don't necessarily know that much about that galaxy. Still, the Milky Way is definitely a spiral galaxy, so it probably looks like all the rest of them. They look pretty similar to each other. If you want to imagine an analogy as to why it's hard to see the Milky Way, imagine that you were trying to figure out the structure of your own body, and all you could learn about your body came from having one eyeball attached to one freckle, and only being able to clearly see the stuff that's visible to that freckle. That's a similar situation that we have trying to learn about the Milky Way from the solar system. Stars come in different colors. Stars come in different brightness. And the word brightness to an astronomer means how bright something looks when we look up at the night sky and see it. If we're thinking about the total amount of light that's coming out of the star, if you're right next to it and you actually measure it, we would use a different word. We use the word luminosity. And messing up brightness and luminosity is an understandable thing to do. I occasionally make the mistake myself. I hope you will catch me if I do during this class. Nonetheless, they are entirely different concepts. Brightness means how bright does a star look when we look up on the planet Earth? Luminosity means how much light is that star putting out total. So here's a point at which we'd have a discussion. Can anyone give me a reason why one star might appear brighter than another? Ideally, you would be watching this recording while chatting with or in a Google chat room with a friend, and so you can have these brief discussions. And I hope that many of you will do that. But since there's really nobody here, I'm just gonna jump to the chase and say that one star might appear brighter than another because it's flat out more luminous, it's putting out more light, or because it's just closer. And those are the two major factors that determine how bright a star is in the night sky. Even a very bright light can appear dim when you're far away from it. So it's safe to sit in a stadium and look at the football players and look at the lights. But if you were to walk right up to one of those lights and put your face in it, you would be extremely uncomfortable and might actually suffer some form of eye damage. So I'm going to give you a nice, pretty nebula to look at while we demonstrate this. And I'd like everybody in the class to do this activity. Place your thumb at arm's length in front of you and close each eye in turn. Look at where your thumb is positioned in relationship to this nebula. It should move. Now hold your thumb closer to your face. Does does it appear to move back and forth more or less relative to your closer thumb? And I'm going to walk in front of the camera to demonstrate. So, holding my thumb out, and holding my eyes closed, up. And I'm looking at, well, in real life, I'm looking at a faucet. You should be looking at a nebula. There it is. So, I'm looking at a faucet. We're looking at a nebula. I'm alternating with eyes closed. I'm going to bring my thumb way closer. And open and close both eyes. I'll then both alternating. One of these thumbs should be moving more than the other, either the closer thumb or the farther thumb. And repeat this activity until you have figured out which one it is. So when you open and close your right and your left eye, respectively, you see the object move. This is called stereoscopic vision. We don't think of people necessarily as being tremendously gifted animals. Like tigers have claws, cheetahs are fast, whales can generate subsonic sounds and live longer than we do, so on and so forth. But there are indeed certain things that the human species is great at, and stereoscopic vision is one of them. Most other animals do not have anywhere near as good a sense of how far away something is and what their relationship to it is. Most animals, even if you gave them a hand and a thumb, couldn't throw and catch a ball, but almost every person can. So now you can do this with your thumb. It might be a little bit better to grab a couple of pens and do it with that. So I don't have a couple of pens, so I'm going to go back and use my thumb again. And I'm going to hold out both thumbs. Right thumb and left thumb. Open and close my right and left eye alternate while focusing on the distant object. And hopefully by this point it's really obvious that your closer thumb is moving by a greater apparent amount than your further thumb. By comparing the view that's coming out of your left eye to the view that's coming out of your right eye, your brain is able to generate on the spot a pretty accurate picture of how far away things are. Of course, how do astronomers use this? So the name for what your brain is doing is reckoning by parallax. But do astronomers have two telescopes side by side and they alternate which one they're looking through? No, they don't. What astronomers do is this. Here's the source. Sun's in the middle. We're interested in some star that's real far away. So the Earth is on one side of the solar system. Say in June, you take one measurement, and then you just let it do its thing. Oh, that's clockwise, not counterclockwise. I apologize. You let it do its thing, goes around the star, and you take a look from the other side of the solar system. This is analogous to the left eye. And this is analogous to the right eye. And since it's like 7.5-ish light minutes from the sun to the Earth, we get about 15 light minutes worth of separation. It's a pretty big distance. Imagine if I had 15 light minutes between this eye and this eye. I'd probably be pretty good at using parallax. The further apart your eyes are, the better your brain can reckon parallax from. Or in the case of astronomers, the better a computer can reckon parallax from. So we compare the star that we're interested in against things that are truly, truly, really far away. And there are objects that are truly, truly, really far away. The earliest galaxies were, many of them, quite luminous. These are called quasars. And if you're looking at a quasar, you can be pretty confident that it's close to the edge of the visible universe. So quasars aren't going to move at all. You measure how much star A and star B move relative to those background extremely distant objects. And right off the bat, you know that star A is closer than star B. And if you do a little bit of math, you can actually figure out how far away both of those stars are. I'm not going to make you do that math, but I will show you in a slide or two. But first, let's observe this applet. So, where's that boat? Well, it's sitting out there in the lake somewhere. I'm going to take a measurement from this position. I'm going to walk over here, take a measurement from this position. After I have these two measurements, left eye, right eye, or one side of the solar system, other side of the solar system, I can go ahead and use math to determine precisely where the boat is. And this is basically how your cell phone knows where it is, because it is taking measurements off of satellites in orbit around the Earth called GPS satellites. This is how shot trackers on campus work. You know, you got a bunch of microphones set up around campus. And if there's a gunshot somewhere, all those microphones compare information, pass them on to each other, and all of a sudden the police know exactly where the gun was fired. Give or take. So parallax is extremely useful, and it's something we use all the time on Earth. It's not just for astronomers. So turn to a blank page. I'd like you to, in your notes, draw a picture entirely on your own that demonstrates parallax of a closer and more distant object. So just pause this video, draw that picture. Normally we would be screen sharing and talking to each other, and I would solicit feedback, but since this is a recorded lecture, that's not going to happen. So this is the mathy bit that you don't have to understand, but you can measure the parallax angle. You know the distance from the sun to the Earth. And if you've got an angle measurement and one side of a triangle, then you can figure out how far away things are. Parallax angles are tiny in astronomy. We have to go and measure extremely small amounts of parallax. Astronomers are lucky if they can get 2 or 3 arc seconds worth of difference in where a star is from one side of the solar system to another. So there's 350 degrees in the circle, you know that. And there's 60 arc minutes in every arc second. This is the 60 arc minutes in every degree. So now there's 360 times 60 arc minutes in the circle. And there's 360, and there's 60 arc seconds in arc minutes. How big is an arc second? This big. I'm holding a strand of hair in my arm, an arm's length. I'm guessing, even though this is a much better camera than I have at home, you can't see it. So astronomers have to do measurements that are, if they're lucky, about the angular size of 3 or 4 strands of hair. 3 or 4 teeny tiny measurements. And so this technique is really only useful for stars that are relatively nearby in the cosmic sense. So a star at a distance of 1 parsec has a parallelic angle of 1 arcsecond. This is the only time I'll mention the unit of parsecs. Sometimes you'll hear it in science fiction. A parsec's about 3 light years, whatever. It's one of those astronomy specific units that you don't really have to worry about. And I want you to know what a light year is. I don't really care too much if you know what a parsec is. So if something is 3 light years away, it'll have a parallaxic angle of 1 arcsecond. That's 1 strand of human hair held in the narrow dimension at arm's length. Or an alternate way of looking at it is how big a golf ball would appear if you were looking at it from 5 miles away. I cannot see a golf ball from 5 miles away. The same way I can't really see the strand of my hair when I hold it at arm's length. Fortunately, astronomers have computers for this. We didn't measure the first stellar parallax until 1838. It took us that long to actually get good enough equipment to determine for real how close the closest stars are. Now, proper motion is different. With parallax, the star appears in a different spot when you're on one side of the solar system than when you're on the other side of the solar system. But if you wait another 6 months to get back here, that star is going to be in the same spot when June rolls back around. Proper motion is what astronomers observe when a star is actually moving fast relative to us in relatively close by. One of the closest stars to us is Barnard Star. I can't tell you to pick it out of the night sky because it's one of the dimmest stars out there. Because it's so not luminous. But it is whipping by us. Here you see Barnard stars relative to the background stars. Barnard Star is moving really fast relative to Sol, and is going to whiz by us and go on its merry way. Hopefully humans will get there before it completely gets out of our neighborhood, because it's sort of an interesting M-class star. A lot of stuff there to find out. So now with all this stuff that we learned from astronomy, we can occasionally determine what things' true velocity is. You get the velocity away or towards our solar system using red shifting and blue shifting. And that's very precise. Only if a star is close enough to show proper motion can we measure the transverse velocity, the velocity that's not towards or away from us. And it's those two speeds together that make up the star's real velocity. Because transverse velocity is so difficult to measure, we, as astronomers, are in a ridiculous situation where we often do not know how fast things are really moving. We know how fast they're moving towards us. We know how fast they're moving away from us. Quick examples. One of the closest stars to us is the Centauri systems. So there's 2 stars, Alpha Centauri and Beta Centauri, and they're in orbit around each other. There's a 3rd star called Proxima Centauri. It's much fainter, and we're not sure if it is gravitationally bound to Alpha and Beta Centauri. In other words, we're not sure if Proxima Centauri is truly part of the Centauri star system or if it's just passing by. An example that is to me even more ridiculous is that the Milky Way has 2 dwarf galaxies nearby, the Greater and Lesser Magellanic Clouds. You can't see them from the northern hemisphere, unfortunately. You're gonna have to go to Australia or Chile to see them in the night sky, but they look more or less like Andromeda. There's like a little fuzzy brightness against the night sky. Astronomers aren't sure if the Greater and Lesser Magellanic Clouds are in orbit around the Milky Way, or if the Milky Way is going to rip them up or if they're passing by the Milky Way and they're going to continue on their own motion. Because we know precisely what their velocity is towards or away from us, but we just haven't watched them for long enough to measure their transverse velocity. In the 1990s, a space satellite called Hipparchus observed the parallax of 1,000 to 120,000 nearby stars, enabling astronomers to measure the distance to these stars. Google Chrome uses data to construct a 3D movable model of these nearby stars. Let's check it out. And I hope that you will check this out on your own computers. So there's our local stellar neighborhood. And with satellite measurements, we can get pretty good picture of where things are that are nearby. And my scrolling is not working. Aha. Closer you get, the better the data gets. So here's our real stellar neighborhood. The stars that are very close to us. There's Sol. There's Pollux. There's Barnard Star, the one that's zipping by us. Alpha Centauri has got to be here somewhere, but I'm not seeing it. Oh. My little laptop. I'm not sure why it's not rendering the names here, but that should be Alpha and Beta Centauri. And Proxima Centauri is pretty faint, so it may not be indicated. Or maybe Google made a mistake and they just didn't include them. But I think that's Alpha and Beta Centauri. The further out we go, the more guesswork is involved. Until at a certain truly far away from our sun. When you get out to the size of the whole galaxy, it's completely made up. We can't even clearly see the other side of the galaxy. But still a cool thing to explore. There is your immediate stellar neighborhood. Oh, great. I'm hopeful that you can still hear me. My computer has frozen and I'm looking at a spinning circle. Zoom controls.